This video is on the variable oxidation states of transition metals. And in this video we need to understand how chromium 3 and chromium 2 are formed by reduction of dichromate ions with zinc. Know the redox titration of iron 2 with manganate ions and dichromate ions and perform calculations using the equations for these reactions. Know the oxidation of cobalt 2 with air in ammoniacal solution. And know the oxidation alkaline solution of cobalt 2 and chromium 3 by hydrogen peroxide. Before we can tackle this aim, we need to understand what the dichromate ion is. So in Chem 2 we come across potassium dichromate, which has the formula K2Cr2O7. Now when we're writing redox equations with the dichromate ion, we will not include the counter ion, which is the potassium. So the dichromate ion is Cr2O7 2-. Now this gets reduced with zinc to form chromium 3+, and then the chromium 3+ gets reduced further to form chromium 2+. The dichromate ion is an orange colour, so I'm going to draw it with an orange colour. And when it gets reduced first by zinc, it goes to make Cr3+, which has a green colour, and you'll recognise that colour change, as I said, from the oxidation of alcohols. To balance this, we just use our rules for balancing half equations. So first you balance anything that's not oxygen or hydrogen, so that's the chromium. Just going to put a 2 in front of the chromium 3+, because there are 2 chromiums on this side and only 1 on this side. Then we need to balance the oxygens. There are 7 on this side, and therefore we balance the oxygens with water. So you need to add 7 H2O onto this side. That's a 7. Then we need to balance the hydrogens with H+. There are 14 on this side. There are none on this side at the moment, so we need to put in 14 H+. And then we also need to balance the electrons. Now, on this side, there is an overall charge of 2 times 3+, and so there's a 6+ charge overall on this side. On this side, there's an overall charge of 12+, because there are 14 pluses from the 14H+, and there's a 2- charge from the dichromate ion, so that makes this 12+. So, to balance these two sides out, we can bring this 12+ down to 6+ by adding 6 electrons on the left-hand side. So on this side we'll also have 6 electrons. The zinc will get oxidized to zinc 2+ and 2 electrons. And so when we multiply these two things together, or add these two half equations together to make the full equation, first we need to multiply this bottom equation by 3 in order to get 6 electrons on the zinc equation. And then we add them together. So overall we get 3Zn plus 14H plus Cr2O7 2- goes to make 2Cr3 plus 7H2O plus 3Zn2+. And you'll see a colour change, as we've said, from orange to green for the chromium 3+ ion. What then happens is the chromium 3+ is reduced further by the zinc to form chromium 2+. So if I just delete all this, so we've got chromium 3+, which is a green colour, and that goes to form, that's reduced further to make chromium 2+, which has a blue colour. And then to balance that, we just need to add an electron onto the left-hand side to bring both of the charges down to 2+. And then the zinc will get oxidized again to zinc 2 plus 2 electrons. So then all we need to do here is multiply the top equation by 2 to make sure the electrons cancel, and so what you get then is zinc plus 2 Cr3 plus goes to make 2 Cr2 plus zinc 2 plus. And the colour change here is green to blue. You do need to know all these colours of the ions that I am pointing out in this video. So another two redox equations that you need to know are the redox equations between iron 2 and manganate ions, and redox reaction between iron 2 and dichromate ions. I'm going to start with iron 2 and manganate ions. So you need to know what the manganate ion is, and that is MnO4-. And when that gets reduced, it forms Mn2+. And then if we just balance this, so the Mn's are already balanced, you need to balance the oxygens by adding 4H2O on the right hand side. Then balance the hydrogens by adding 8H+ on the left hand side, and then balance the charges. So on this side you've got 8H+, take away 1 for the manganate ion, so you've got 7+ on this side, you've got a 2+ charge for the manganese ion on this side, so you need to add 5 electrons on the left hand side to bring this side down to 2+. And then you've got the iron, so the iron 2+ gets oxidized to iron 3+, plus an electron, and then we need to multiply this up by 5 to make sure the electrons cancel, and so our overall equation for the reduction of manganate ions by iron 2+ is 5Fe2+ plus 8H+ plus MnO4- goes to make 5Fe3+ plus Mn2+ plus 4H2O. And it's the ratio between the iron 2+ and the manganate ions, or any of them to be honest, they could ask you a question about any of this, that will be used if you're asked a question on this. The other reaction is between dichromate ions and iron 2+. So dichromate we've come across in the previous slide, so we've got Cr2O7 going to make Cr3+. Balance CRs first, that's 2 Cr3+, then balance the oxygen, so 7H2O on the right hand side, then balance the hydrogen, so 14H+ on the left hand side, and then balance the charges again, so there's 6+ here, 14+ take away 2, that's 12+ here, so we need 6 electrons on this side. We've got the iron 2+ turning into or being oxidized to make iron 3+ plus an electron. We need to multiply the iron equation up by 6 to make the electrons cancel, and so overall here we get 6Fe2+ plus 14H+ plus Cr2O7 goes to make 2 Cr3+ plus 6 Fe3+ plus 7 H2O, and again the ratios between these is what you need to be able to use in order to answer questions on this, which we're going to have a look at now. So here's the sort of question that may be asked based on those equations, and at first glance it seems pretty daunting. So we'll just read through it. So a solution of iron 2 sulfate was prepared by dissolving 10 grams of iron sulfate in water and making up to 250 cm cube solution. The solution was left to stand exposed to air, and some of the iron 2 ions became oxidized to iron 3 ions. A 25 cm cube sample of the partially oxidized solution required 23.7 cm cubed of 0.01 molybdenum cubed potassium dichromate solution for a complete reaction in the presence of an excess of dilute ferric acid. And asked you to calculate the percentage of iron 2 ions that have been oxidized by the air. So the first thing to do with any of these sort of questions is to write out the equations. So at the end they did a titration. This is a redox titration between dichromate ions and the iron 2 ions that were left over. So what you'll have is the dichromate, Cr2O7, 2-, going to form Cr3+, balance the chromium, balance the oxygen, balance the hydrogen, balance the charge, and you got your Fe2+ being oxidised by the dichromate ions to Fe3+. This is the Fe2+ that you have left over after it had been left to stand in air, plus an electron, multiply this up by 6. And then there's no real need to combine these because you can see that the ratio between dichromate ions and iron 2+ ions is 6:1. So the next thing to do after this is to work out number of moles of something. We can work out number of moles of the dichromate that was used in the reaction, because it says that we've used 23.7 centimeters cubed of 0.01 molybdenum cubed potassium dichromate. So we can work out moles of the dichromate ions, Cr2O7 2-. Whenever you do a question like this, always label your numbers, say what your numbers mean. So that's what I've done here by putting this in brackets. And that's going to equal 23.7 divided by 1,000 times by the concentration, that's volume, times by the concentration, which is 0.01, and that gives us 0.0000237. And then from the ratio of 6:1, we can work out how many moles of iron 2+ there were left in the 25 centimeter cubed sample. So we can work out moles of iron 2+ in 25 centimeters cubed by timesing the number of moles by 6, so 0.0000237 times 6, and that gives us 0.001422. And then it tells us at the beginning of the question that this iron 2+ solution was made up in 250 centimeters cubed. So to work out how many moles of iron 2+ there were in 250 centimeters cubed, we have to multiply this by 10. So moles of iron 2+ in 250 equals 0.001422 times 10, which equals 0.01422 moles. We can then work out how many moles of iron 2 there were originally by working out the number of moles by dividing mass, 10 grams, by the MR, 277.9. So that's going to equal 10 divided by 277.9 equals 0.03598. So your two numbers you've got here are the number of moles of Fe2+ that were in the solution originally, and then this is the number of moles of iron 2+ left in the solution after being exposed to air. Now the question, if you go back to what they actually ask you, is calculate the percentage of iron 2 ions that had been oxidised by the air. So this is how much that has been left. So all we need to do is work out how much has been oxidised. So to do that, or the percentage to do that, we're going to do 0.03598 take away 0.01422. That tells us how many iron 2 ions were oxidised, but then divide that by how much was there at the beginning, 0.03598, and then times it by 100 to give us a percentage, and that gives us the answer, which is 60.5% to 3 significant figures. So another redox reaction you need to know about is the oxidation of cobalt-2 in air to form in ammoniacal solution. So what I'm going to show you first is how we get from cobalt hexaaqua to the ammonia complex, which is basically what it means by being an ammoniacal solution. So we start with the cobalt tetracca complex, 2 plus, and we just add a little bit of ammonia, which is a base, so we'll need 2 of them to balance this. We'll first form the hydroxide, so cobalt with 4 waters and 2 hydroxide ions. So that's a precipitate now because there's no charge on that. And you'll also form 2 ammonium ions, NH4 pluses, because the NH3s, the ammonias, have stolen an H plus from 2 of the water molecules that are datively bonded to the cobalt. Then if we add excess ammonia, the hydroxide will dissolve, you'll need 6 ammonias, and you'll form your cobalt 2 plus ammonia complex. So it's cobalt with 6 ammonias, and that's going to be a 2 plus charge, plus 4 waters that have been kicked out, plus 2 hydroxide ions that have been kicked out. Now it is this complex here which gets oxidised in air when it's left standing in air, basically. And what happens is the cobalt with the ammonias around it, 2 plus, will just get oxidised to cobalt 3 plus, so you'll just form a different complex with a different oxidation state, still 6 ammonias. And what we'll need to do is write 2 half equations for this reaction and then combine them to show the full equation. So first we just need to add an electron to the right hand side to balance the charges. Now this is reacting with oxygen to do this. So the other half equation is oxygen goes to make something. Now it's not completely obvious what it makes at first. So what we're going to do is just balance it as if it's in acidic conditions first. And that means the normal way of adding waters, then H pluses and so on. So what we can do is add 2 waters to balance the oxygens, then 4H plus, and therefore 4 electrons. Now this half equation is not correct, and the reason for that is that ammonia is a base, or an alkali, which is a base that dissolves, and so this isn't the equation we'd have to use because this is in acidic conditions, but actually this reaction is happening in basic conditions or alkaline conditions. So we're going to have OH minus in this equation rather than H plus. So all we're going to do is add OH minuses to both sides to get rid of the H pluses. And when we do that, what we'll form is water with the OH minuses, and we'll just get OH minus on this side. So to do that, we need to add 4 OH minus onto this side, and we need to add 4 OH minus onto the left-hand side. And what that will form is 4 waters on this side, so the 4 H pluses combined with the 4 OH minuses, so those will cancel out and you'll make 4 H2O, which will then cancel with the 2 H2O on the right hand side, so those will cancel, and actually what you'll be ended up with is 2 H2O on this side. And that is your other half equation for this reaction, so 4 electrons plus 2 H2O plus O2 goes to make 4 OH minus. We can then combine these by multiplying up the cobalts and the electrons by 4 to make the electrons cancel, and so overall what you'll get for this reaction is 4 cobalt with 6 ammonias around it, 2 plus 2 H2O plus O2 goes to make 4 cobalts with 6 ammonias around it, 3 plus 4 OH minus. So another 2 equations you need to know are the oxidation in alkaline solution of cobalt 2 and chromium 3 by hydrogen peroxide. So we're going to do cobalt 2 first just because it's very similar to the one on the previous slide. So we're going to use the cobalt with 6 ammonias around it, the ammonia complex, because that basically is, well, it is cobalt in an alkaline solution because ammonia is alkaline. And that will turn into cobalt, with ammonias around it, 3+ instead, being oxidised, and then we need to add an electron on the right hand side in order to balance it. And then we've got hydrogen peroxide, and it's not completely obvious at first what it turns into because it's not really given to us. And so what we'll do is balance it as if it's an acidic solution first, which is the way we know and what we saw on the previous slide. So first we'll balance the oxygens with 2 waters, then we'll balance the hydrogens, so we need 2H+ on the left hand side, and we'll also need 2 electrons. Then we need to convert it into alkaline conditions, so we're going to add 2OH- onto the left hand side and 2OH- on the right hand side, and what will happen is these 2H+ will combine with the 2H- to make water, and those will cancel with the 2 waters on the right hand side. And so those are our 2 half equations. We just need to multiply up the top equation by 2 in order for the electrons to balance, and so what we get is 2 of the cobalt ammonia complexes plus H2O2 hydrogen peroxide goes to make 2 of the 3+ complex plus 2OH-. The chromium-3 equation is slightly more complicated. So we're going to look at that now. Let's just see if I can delete some of the stuff that's already there. No, I can't. I'm just going to write it underneath. So, first off, we need to know what the complex is that chromium-3 forms when it's in alkaline conditions. So, if we start with the chromium-3 plus hexaquarine, and then add excess sodium hydroxide, what we end up with is chromium with 6 hydroxide ions around it, and that's one of the complexes you need to know. And the charge will be 3-. And when this gets oxidised, it turns in alkaline conditions to the chromate ion, CrO4 2-. The reason for that is that in alkaline conditions, the dichromate-chromate equilibrium is shifted onto the chromate side, whereas in acidic conditions, it's shifted onto the dichromate side. And you'll see that in a different video. I explain that more fully. So we need to balance this half equation. We'll balance it first as if it's in... just move this over a little bit. As if it's in acidic conditions, as before. So chromium's already balanced. We'll balance the oxygens with water. There's 6 on the left-hand side. There's 4 on the right-hand side. So we need to add 2 H2O. We then need to balance the hydrogens. There are 6 on the left-hand side, and there's only 4 on the right-hand side, so we also need to add 2H+ onto the right-hand side, and then electrons, there are 3- here, there is overall charge of 0 on the right-hand side, and so we also need to add 3 electrons to balance the charges. To turn this into alkaline conditions, we then need to add OH- in order to get rid of those H+. So we need to add 2 OH- to get rid of these H+. So we're going to add 2 OH- onto the right-hand side, and therefore also 2 OH- on the left-hand side. These will cancel to form water, 2 of them, which will add to the water that's already there, so we'll have 4 H2O instead of 2, and then that is balanced. We've then got the hydrogen peroxide equation already given to us up here. We're just going to write that out again underneath. So we've got 2 electrons plus H2O2 goes to make 2 OH-. And then we need to make sure the electrons cancel now. We've got 2 on the bottom and 3 on this one. So you need to multiply the top equation by 2 and the bottom equation by 3 in order to make the electrons cancel. So what we'll get on the top equation, if we multiply it all by 2, if I do the new numbers in a different colour in red, we'll have 4OH minus plus 2 CrOH63 minus goes to make 2 chromate ions plus 8 H2O and 6 electrons, and on the bottom we'll multiply by 3, so we've got 6 electrons plus 3 H2O2 makes 6 OH minuses. And then we need to add these two equations together to form the final equation. So what we'll have is 4OH minus plus 2 of the chromium complex plus 3 H2O2 goes to make 2 chromate ions plus 8 H2O plus 6 OH minus. And then you'll see there's OH minus on both sides, so we'll cancel out these 4 on this side with the 6 on this side, so I'll just have 2 OH minus left over on the right hand side. And that is our equation for the oxidation of chromium 3 plus in alkaline solution by hydrogen peroxide. So we're going to finish off with a few past paper questions. So in this question it says hydrogen peroxide is used an oxidizing agent for the preparation of transition metal complexes. Consider the following reaction scheme. All the complexes are in aqueous solution. So you've got to identify a reagent for reaction 1 and describe the colour change that occurs. So to work out what we need for reaction 1, we can use both the start and the end complexes to help us. This middle complex is going to be the reduced version of this complex, if you like, so CONH36 2+ rather than 3+, because this has been oxidised by the hydrogen peroxide. And so in order to turn this into what this will be, which is CONH36 2+, we will need excess ammonia. And then it says, describe the colour change that occurs. Now, it's important that you recognise when it wants, you read the question very carefully. And when it says colour change, it wants the beginning colour and the end colour. So this starts as a pink solution, which is your cobalt hexareactor complex, and it turns into a yellow solution, which is this complex in the middle, the cobalt 2 complex. And the colour of the final solution formed in reaction 2, when the yellow solution gets oxidised, it turns into a brown solution. So brown is the final colour. And then finally, consider the following reaction scheme. All the complexes are in aqueous solution, again. So for reaction 3, state the colour of the initial and of the final solution and write an equation for the reaction. So that's this one here. So the beginning solution, the chromium hexareactor complex, is ruby red. We don't need to say it's a solution because it does say it's solution in the question, but it won't harm. So it starts as a ruby red solution, and then the chromium 3 complex that is formed is your chromium with excess OH minus or excess NaOH. It's 6 OH minuses and then a 3 minus charge on the complex, and that has a green colour, so it's ruby red to green. And then the equation for reaction will be the chromium hexareactor complex 3+ plus, don't include the Na, we'll just write the OH minuses, so it's going to be 6 OH minus, and that then goes to form your chromium with 6 OHs around it, and that's going to be a 3 minus charge rather than 3 plus, because your OH is negatively charged, and there's 6 of them, and the chromium is 3 plus, so overall that'll be 3 minus, and that's very important that you remember to check the charges. And then you're also going to get 6 H2O. And then the second question, write a half equation for the reduction of hydrogen peroxide to hydroxide ions. Deduce an overall equation for reaction 4 and state the colour of the final solution. So hydrogen peroxide, it tells you it's forming hydroxide ions. So to balance this, we'll need 2 hydroxide ions, and we'll need 2 electrons on the left hand side, and then an overall equation for reaction 4, so we're also going to have to write an equation for this chromium with 6 hydroxide ions around it, this complex here, turning into the chromate ion, which we've looked at before. May as well do it again then, though. So we've got the chromium with 6, 3 minus, goes to make CrO4 2 minus. We'll just go through the balancing again. We'll assume it's an acidic solution first and then turn it into alkaline conditions, because remember, for chromate to be formed it must be in alkaline conditions. So we need 2 H2O on the right hand side to balance the oxygens. We also need 2 H pluses to balance the hydrogens, and then 3 electrons to balance the charges. We're then going to add hydroxide ions in order to get rid of the H+. So we're going to add 2 OH-. These will cancel to form waters, so we'll have 4 waters instead. And we'll also have the 2 OH- we added. We have to add OH- on both sides in order to not change anything about the equation, if you like. And then we're going to multiply the top equation up by 3 and the bottom equation up by 2 to make sure the electrons cancel. So I have 6 electrons, 3 H2O2 and 6 OH-, and then bottom one up by 2, so you have 4 OH-, 2 of those, 2 of chromate ions, 8 waters and 6 electrons. Then add these two things together and your final answer will be 4 OH- plus 2 CrOH6 3- plus 3 H2O2 goes to make 2 CrO4 2- plus 8 H2O plus 6 OH-. Then we'll just cancel out the OH-, so have 2 on this side instead, and that's your overall equation. And then it says state the colour of the final solution, while the chromate ion is yellow. So yellow is the last bit of that answer.